Morning, everyone. So today we will go through the module 2, that is gas power cycle. Let's see the contents of this syllabus of this module. So first thing is gas turbine cycle. So basic gas turbine cycle, that is known as a Brayton cycle or Joule cycle. So we will go through description, components, where it is added, where the power is generated, for which process it has been generated, or where the which process it has been rejected. So we will go description of each parts of this gas turbine cycle, that is Brayton cycle, or it is also named as Joule cycle. And then afterwards we will make the analysis, that is especially the net work output and efficiency of this cycle. So after finding out the efficiency, then we will analysis on that efficiency formula. So for which pressure ratio we will get the optimum work output, means maximum work capacity of the cycle, or for which pressure ratio we will get the maximum efficiency. So then afterwards we will go for how we can improve the basic cycle efficiency, that is how we can improve this Brayton cycle efficiency. So three methods, that is direct method, regenerative method, and intercooling method. So these three methods are being used, employed in the gas turbine cycle. So these three methods we will study again. We will analysis on that part, that is network output as well as the efficiency of that team improved implementing the efficiency of the cycle. So next, combination, because alone we can't use, either alone intercooling it is not at all suitable, or alone reheating is also not at all suitable, alone regenerative also not at all suitable. So either we may have intercooling and reheating, or either may we have intercooling or regenerative, or combination of all three, that is intercooling, reheating, regenerating, so that efficiency can be improved a lot, or network output of the cycle can be improved. So finally, after going through all those steps, just a brief introduction about a jet propulsion system. So in this we have the turbofan and ramjet cycles. So these are the contents of the syllabus. Next, we will move on the basic introduction. So totally according to the syllabus, 10 hours are required. After completion of the theory part, we will move on to the problematic point. So minimum of 6 to 7 classes are required to complete the entire syllabus. Next, whenever you talk about the gas power cycle, so we are already covered vapor power cycle module 3 in the class. So in the vapor power cycle, the working fluid is steam. That is, our liquid water will takes the heat from the boiler, and it will convert it into steam. Then the power is generated in the turbine. So steam will carries that energy, and it will transfer it to the turbine, and it will produce us the mechanical work. So in the vapor power cycle, steam is carrying the energy, whereas over here gas power cycle, as the name indicated, the gas, here we will have the working fluid as the gas. So the cycle which operating on the gas for the production of power, such type of cycle is known as gas power cycle. Cycle is nothing but repetitive process of series of process, and it will bring the your working fluid into the original state. So that is called as cycle. That is about a closed cycle. Next, whenever you use gas as a working fluid, we have to make sure that, or in this cycle, there is no phase change will occurs. Whereas in vapor power cycle, liquid water will get converted into vapor state. There is a change of phase with that. So in this cycle there won't be any change of phase So working fluid will be in a almost in a gaseous state only, hence it is known as gas power cycle. So compared to vapor power cycle, there won't be any phase change occurs in the working fluid. So this cycle either may work it on a cycle process or non-cyclic process. That is either you may have closed system or you may have open system. So for a closed system, we have the hot air engine as the working means example. So in this working fluid operate on a closed cycle, whereas in the open cycle we have several example like ice engine. So in the ice engine, fuel has been combustion will take place inside the combustion chamber, then it will transfer the power, then it will send out to the surroundings. So that fluid may not, it won't come back to the initial state, or that fluid may not be used for next cycle, hence this type will be open type of cycle. And for example, in the aircraft also we have the open type of cycle, gas power cycle, where exhaust is left to the surroundings and we are not reusing that exhaust. So and so most of the gas power cycle will be of open type of cycle, except in the power production. Next, while we are analyzing any ideal gas turbine, we have to assume certain things initially. So, what are the assumptions we are going to analyze on the ideal gas turbines? So, first one is the working substance is air or working fluid. In the cycle, we are taken as air, and it will obey the perfect gas equation, that is PV equals MRT. And expansion and compression processes are isentropic, that is nothing but reversible adiabatic process. That means during expansion as well as compression, it won't enter into the system or it cannot be leaving the system. Next, there is no pressure loss. So we have various components in the cycle. So that components is connected by the piping, or there will be bending will be there. So that loss of it is not considering during the analysis of the cycles. So next assumption is the change in the kinetic and potential energy is very small, and so you can neglect that energy, kinetic and potential energy. So of the fluid can be negligible. Next, flow through various component is one dimension flow. We are assuming one dimension flow, and it is steady and it is uniform. So these are the assumption we are going to consider while analyzing your ideal gas turbine cycle. Next, we move on to the basic cycle, that is Brayton cycle. So, simple gas turbine cycle, it consists of, see over here, PV diagram. We will go through the PV diagram and TS diagram. So, Brayton cycle, it is a basic cycle of your gas turbine power plant. So this consists of four processes. In that four processes are 1 to 2, it is the reversible adiabatic compression. So 1 to 2 represent reversible adiabatic compression. After compression, we have the heat addition process. So this heat addition process is taking at a constant pressure. So 2 to 3, it represent constant pressure heat addition. Constant pressure heat addition. Next, 3 to 4. So after your heat added to the system, it has to expand. So 3 to 4 is the expansion process, and that is also reversible adiabatic or isentropic process. So 3 to 4 represent your isentropic expansion process. After expansion, we have the heat rejection. So heat rejection will take place at a constant pressure, that is 4 to 1. So 1 to 2 you have the isentropic compression. Isentropic means S will remains constant. Remember, isentropic means S will remains constant, and 1 to 2 will be straight line in the TS diagram. and 2 to 3 it is a constant pressure heat addition. So hence here horizontal line in the PV diagram and in TS diagram it is like this, 2 to 3 constant pressure process. So at constant pressure it is added to the system. Next 3 to 4 again it is isentropic. In the PV diagram it is like this, and it is expansion and pressure will be decreasing. So temperature decreases, expansion process. So since it is isentropic process, so in the TS diagram it is a straight line. Next 4 to 1 it is the heat rejection process at constant pressure. So in the PV diagram it is a horizontal, in TS diagram it is like this. So these are the four basic process of the Brayton cycle. So whenever you talk about a Brayton cycle, so it consists of two isentropic process and two constant pressure process. So isentropic compression, so 1 to 2 compression and 3 to 4 expansion, isentropic process, and constant pressure process are 2 to 3 heat addition, 4 to 1 heat rejection. So heat addition and rejection are taking place at the constant pressure. Compression and expansion will taking place at the reversible adiabatic, that is nothing but isentropic process. Entropy remains constant. So this is about the four basic process of your Brayton cycle. For process 1 to 2, as I already told, it is nothing but isentropy compression of the air. So working fluid over here it is air in the compressor. So component of this one is a compressor. So compressor will compresses the air from pressure P1 to P2. So during this process work is done by the air, means we have to supply the work so as to compress the air. So here is work is done on the system, on the air by the surroundings. So this is the work input. 1 to 2 is will be the work input. Next we have the 2 to 3 process, that is nothing but constant pressure heating. From the 2 to 3 we are adding the heat. Q is in at constant pressure till maximum permissible temperature is reached, that is nothing but till how much temperature you want maximum, till that you have to add the heat. So this is nothing but constant pressure heat addition process. 2 to 3. Next 3 to 4, what you have? 3 to 4 it is the expansion. Again expansion of the air, because we have supplied the heat, so it carries the energy. Air is carries the energy, and that energy has to be transferred to mechanical work. And so 3 to 4 expansion will take place in the turbine. So 3 to 4 component will be your turbine. So in the turbine work is produced by the system, or work is done by the system. So you are getting the work over here, and the process over here it is isentropic expansion. So isentropic work done. So work will be done by the system. So you are getting the mechanical work during this process. Next, after 3 to 4, we have the 4 to 1, that is the heat rejection process. So, whatever air is there after expansion, it carries some kind of heat. So, we have to bring back the working fluid to the original state. So, whatever the heat is there, that has to be rejected to the surrounding. So, 4 to 1 will be heat rejection process at constant pressure. So, this is how your working of Brayton cycle will be there with respect to all the components. So process 4 to 1, whatever you are talking, is only for closed cycle. So if you are talking about the open cycle like ICNG, then heat rejection process won't be there, 4 to 1 won't be there. So only we have 1 to 2, 2 to 3, 3 to 4. This line won't be there, you should not show. So this is for closed cycle. Remember, you just draw the diagram according to the question. If in the question they have asked open cycle gas turbine means, then you should not show this line, that is 4 to 1 should not be there on the PV diagram as well as TS diagram. Remember, heat rejection process won't be there. So heat rejection process will be there only if you are using that working fluid for another cycle, that is for closed cycle only. 4 to 1 will be that, that is the end process will be there, or else after this it is directly going to the surroundings. And here we are drawing fresh air for the next cycle. So next cycle continues, fresh air drawn and rejecting, fresh air it is drawing, rejecting, like that cycle will continues for open cycle. For closed cycle, same air it is continuing throughout the cycle. This is the difference between open cycle and closed cycle, remember that one. Now we will derive the equation for work done as well as efficiency for this simple gas turbine cycle. So before that, you just check the component. We will have the compressor. For the compressor, we are doing the work. So work is done on the system. Done on the system. So work input, that is WC. Here is drawing at state 1 and it will compresses at which process? It is isentropic process. So isentropic process, air is being compressed to the pressure P2 from P1. Initial pressure will be P1, exit pressure is into P2, the desired pressure what you want. Next, after P2 has been reached, then it is going to the combustor, we will call it as combustor, where is heat is supplied to the system. It is like a boiler or any other equipment, heat exchanger process, where fuel is burned outside and that energy is transferred to your air in the combustor. So this is known as combustor, where you are going to supply the heat to the system, that is QS. Next, this process is constant pressure. So P2 also equals P3. Only heat is added, hence temperature is rising from T to T3. So this is about combustor at constant pressure process. Once heat is added to the system, then it has to produce the work. So it is entering into the turbine at state 3 and the expansion of the air will take place, that is it will transfer the energy from air to the turbine for the production of work. So turbine will produce the work, that is WT. So at which process it is? Once again it is isentropic process or reversible adiabatic process. Work is done by the system. So WT. So it will temperature reduces from T3 to T4. The state is from inlet will be 3, outlet will be 4. This is how your turbine works. Next, after turbine, it is if it is closed cycle, then condenser will come into picture. If it is open cycle, you leave as it is, like this, leave as it is, you don't show this component. So I am showing with respect to closed cycle. So whenever the closed cycle is there, it is going into the condenser. This part is the condenser, it is nothing but heat exchanger. It's similar to your vapor power cycle which you studied in the class. So it will enter into the state 4 and it will reject the heat. So Q will be rejected to the surrounding from the system. So this process, once again, it is a constant pressure process. At constant pressure it will rejects the heat. So it will bring back to the working fluid to the initial condition, that is P1 T1 condition it will bring. So this is how your uh, gas turbine works and various components. So now you know what are the work processes, what are the heat processes. So here work input, heat input, work output, heat output. So these are the four heat and work transfers of the system. To work transfer, to heat transfer will be there. So now we will see one by one. So then we will frame the equation and we will get the expression for Brayton cycle efficiency finally. So this is the ultimate aim of this derivation. So now first we will see. So we have to get the thermal efficiency in terms of pressure ratio. Pressure ratio is nothing but the maximum pressure to the minimum pressure. That is nothing but P2 will be the maximum pressure and the minimum pressure will be the P1. So it is compressing from P1 to P2. So you have to get the expression in terms of P2 divided by P1. That is known as pressure ratio, RP. RP is nothing but the maximum pressure to the minimum pressure. Maximum pressure of the cycle, you can just go through that PV diagram of the previous slide. So maximum pressure will be P2, that is also equals P3, remember, and minimum pressure is P1, that is also equals P4. So pressure ratio is means maximum pressure divided by minimum pressure, that is nothing but P2 divided by P1 or P3 divided by P4, anyone. So that is nothing but pressure ratio RP, and we have to get the efficiency equation in terms of pressure ratio. So first apply SFE equation for all the components. First we will consider about compressor. So in the compressor, what are the inputs? One is state point one, state, then the work is the input and output will be the so like that, using SFE, how you can write WC plus, if you consider mass flow rate, M into H1 plus WC, that is equals M into H2. If you considering M is the mass flow rate of the working fluid. So energy entering the compressor, that is equals energy leaving the compressor. That is how you are going to apply the SFE for each component. So while applying SFE, already in the assumption we told we are neglecting the kinetic and potential energy. So that two terms won't be there in the SFE equation. So that term we are leaving. So only the energy part we will consider. So what you will get WC, that is the input, and M into H1. So we are not considering for unit mass. So some kind of mass M is flowing through inside the system. So M into H1 and output will be the M into H2. Now rearrange the term. So what you will get? WC you will get M into H2 minus H1. So M into H2 minus H1 you will get. So you can write this enthalpy term in terms of temperature, that is H2 is nothing but Cp times T2. Similarly H1 is nothing but Cp times T1. So you substitute that equation in place of H1 and H2, what you will get expression WC is nothing but M into Cp is common, you can take outside, so T2 minus T1. So this is the equation you will get for the compressor. If you want to consider for unit mass, so M will be eliminated. So for unit mass, so whatever the equation is there, just divided by M. So for unit mass, you will get the compressor work input. So that is nothing but Cp times T2 minus T1. So note down this one as equation 1 for mass M, and for if it is for unit mass, note down this one as equation 2. So this is the expression you can write for a compressor. So similarly you can write same way you can write the expression for turbine as well as supply of heat, that is the combustor, and next one is for a condenser. So same way you can apply the SFE equation for each component of the Brayton cycle. Then finally we will write the expression for net work done and efficiency. So next we will go for the turbine. So in the turbine, so what we have, input will be 3 and output will be 4 and WT. So while writing WT, input is M into H3, that is equals W2 into M into H4. So what I will get from WT is nothing but M into H3 minus M into H4. Just rearrange. So you will get WT is M into H3 minus H4. So once again H3 you represent into temperature, that is nothing but H3 is nothing but Cp times T3 and H4 is nothing but Cp times T4. Cp is common, you can take it outside, so you will get Mcp times T3 minus T4. So this equation you will get for mass M of working fluid for the turbine work. So this equation you note down as 3. If it is for unit mass, so what you have to write, this one divided by M. So divided by M you will get for the expression for turbine work for unit mass. So unit mass you will get Cp times T3 minus T4. So note down that one as equation 4. Similarly you write expression for QS. So what are the inputs? input is at 2 and QS, and output is 3. So how you can write M into H2 plus QS, that is equals M into H3. So QS is becomes M into H3 minus M into H2, or M into H3 minus H2. So this is the equation you will get while applying SFE for a combustor or combustion chamber. So note down QS is nothing but M into H3 minus H2. Again, you represent H3 and H2 in terms of temperatures. So Cp into T3 minus Cp into T2. So Cp will be common. You can take it outside. T3 minus T2. So note down equation as a 5. So for unit mass, you will get, so whatever the equation you got, just divided by M. So you will get expression like this. Next, after getting the expression for heat input, heat rejection not needed, not that much necessary. So you can write also, no issues. Note on, you can, if you want, you can note on the apply the SFE. So input will be the 4, output will be the QR and 1. So how you will get M into H4, that is equals QR plus M into H1. So QR will be M into H4 minus M into H1, or M into H4 minus H1, like that you will get for QR. So again you can write that in terms of temperature. So we will get M into Cp into T4 minus T1. So that is the expression you will get for a condenser. So now after getting all the expression, so network you have to find out. Network means whatever the output is the minus input. So that is the network done by the system. So turbine work minus compression work. So that is the W network you will get. So for unit mass, W network is equal to WT minus WC. So WT expression is there for unit mass. Similarly, in the last slide we have the expression for WC. So note down that equation and write the expression for network output. So you will get Cp times T3 minus T4 minus Cp times T2 minus T1. That is the expression for W net you will get. Once you got the expression for network, then efficiency formula is AC. What is the efficiency formula? In general case of any power cycles, eta is nothing but the net work done divided by supplied heat. So that is the output by input. So output is the net work done and input is your how much heat is supplied. That is the energy input you are going to your working fluid. So next we will note on the efficiency formula. So this is the net work done formula. Next we will move on to the efficiency. Just note down the PV and TS diagram rather than the your flow diagram. So efficiency, it is given by net work done divided by heat supply. So now you know the formula of net work done as well as heat supply, that is nothing but QS or Q1, whatever might be. So just substitute that one. So in this thing, Cp is common and T3 minus T4 will be there. So rearrange the term. Once you got the value of Cp cancels. So once the Cp will get cancelled, next we will make T3 minus T2 and you bring over here, so you will get T4 minus T1 minus T4 minus T1. So this will term gets cancelled. You will get the expression 1 minus T4 minus T1 divided by T3 minus T2. So this is the expression you will get efficiency of the Brayton cycle. So once you got the efficiency of the Brayton cycle in terms of temperature, next you have to get the expression for a Brayton cycle in terms of pressure ratio. How you have to get? For that reason, you should use the relationship between temperature and pressure for the process 1 to 2 as well as 3 to 4. So once you use that relation for this 1 to 2 and 3 to 4 relationship between temperature and pressure. So now for 1 to 2, if you want to uh, write the expression which relates between temperature and pressure, how you can write? T2 divided by T1, that is equals P2 by P1 to the power gamma minus 1 by gamma. So you can write expression for this temperature and pressure. So here I have considered so T2 here, T2 by T1 is nothing but P2 by P1 to the power gamma minus 1 by gamma. This is how you can write the expression for our relationship between for temperature and pressure for the process 1 to 2, because we have assumed the working fluid is air and it obeys the perfect gas equation. Once it obeys the perfect gas equation, that has to satisfy this equation also, that is the relationship between temperature and pressure. Next, once you remember this one for this process, then next a similar way 3 to 4 will be there. So 3 to 4 you can write T3 by T4, that is nothing but P3 by P4 to the power gamma minus 1 by gamma. But in the expression we can write P3 also equals P2 and P4 also equals P1. So we have written P2 by P1 only for the gamma minus 1 by gamma for the process 3 to 4. Remember how you got P2 by P1, that is P3 is nothing but P2 and P4 also nothing but P1, and so you can write T3 by T4 also P2 by P1 to the power gamma minus 1 by gamma. So in this way you can write the expression for T2 by T1 and T3 by T4 in terms of P2 by P1. So both the cases we have P2 by P1, means both this one the right hand side is same. Now we will define one term, that is nothing but the pressure ratio. So what it means, pressure ratio? Pressure ratio is nothing but the maximum ratio of maximum pressure to the minimum pressure, that is nothing but the pressure ratio, and it is denoted by Rp. So what you have the expression for Rp now? Rp is nothing but P2 by P1, the maximum pressure P2 by P1, that is also equals P3 by P4. So hence you can substitute instead of P2 by P1 or P3 by P4, you can substitute Rp. So here you will get Rp, here also you will get Rp. So what expression you will get after substituting Rp over here? You will get T2 by T1, T2 by T1, that is also equals 3 by T4, that is equals Rp to the power gamma minus 1 by gamma. So from this equation what you will get? T2 is nothing but T1 times Rp power gamma minus by gamma. Similarly in this equation, if you compare this equation, then you will get T3 is nothing but T4 times Rp to the power gamma minus 1 by gamma. So now in the efficiency equation, if you see the efficiency equation, how it is, eta is nothing but 1 minus T4 minus T1 divided by T3 minus T2. So in the denominator we have T3 minus T2. So instead of substituting in terms of T3, so you have to substitute T3 in terms of T4 and Rp, and similarly T2 also you have to substitute in terms of T1 and Rp. So substitute that one in the efficiency equation, that is in the equation 5. So once you substitute that one, so this is the your T3 term. So T3 is nothing but T4 times Rp to the power gamma minus 1 by gamma. So T3 is over. Similarly T3 minus T2 was there. So T2 is nothing but T1 into Rp to the power gamma minus. So you got like this. Now over here in the denominator, which is the common? Rp to the power gamma minus 1 by gamma is common. You can take it outside. What you will get over here inside the bracket? T4 minus T1. That means that you can eliminate. So simplify that one and get the final expression for Brayton cycle. That is nothing but Brayton efficiency is given by 1 minus 1 divided by Rp to the power gamma minus 1 by gamma. This is the expression for Brayton cycle efficiency. Remember this one, Brayton cycle efficiency. It is given by 1 minus 1 divided by Rp to the power gamma minus 1 by gamma. Therefore, your Brayton cycle efficiency, that depends upon your pressure ratio. So this expression you might have gone through in module 1. Module 1 auto cycle was there. So auto cycle also having the same kind of expression. You just check that auto cycle efficiency. There you are written eta is nothing but 1 minus 1 divided by RV to the power gamma minus 1 by gamma, where RV represent over there compression ratio. So the efficiency formula for Otto cycle as well as Brayton cycles are similar. In the Otto cycle, it depends on compression ratio, whereas your Brayton cycle, it depends on pressure ratio. Understood? So this nothing but if you keep on increases the RP value. So if you increases this RP, what will become this entire thing, because it is in the denominator, so 1 by denominator will reduces. So this part is reduced means efficiency is going to increase. So as RP value increases, the efficiency keep on increases up to certain limit. After that limit, so there won't be a much change in the efficiency. Means if you increase furtherly RP after that limit, say 5 or 4, then there won't be much change in the efficiency. The rate of increase in the efficiency may decrease after the certain value of RP has been achieved. So this is how you will find out effect of RP on the efficiency. So this is about your Brayton cycle work done and its efficiency. So next, this derivation is very important. You have to study that one. So already I have told it in class, just for remembering purpose. Now we have to just revising this portion. Next, we will go for another derivation that is the very important from the exam point of view. That is to get the expression for optimum pressure ratio for maximum specific power output in terms of maximum and minimum temperature of the cycle. So which pressure ratio will give the maximum work output for this Brayton cycle? So in terms of maximum temperature is T3 and minimum temperature is T1. You can just look into this TS diagram. So in this TS diagram you can see the maximum temperature is T3 and minimum temperature is T1. So you have to give the expression for RP, that is optimum RP, when the power output of the cycle is maximum, which will be in terms of T3 and T1. So you have to give the expression of RP in terms of T3 and T1 when the power output is maximum. So for that, first you need to know the net work output. So already you have gone through. So directly I will write. So in the exam you write separately, then you get this expression. After getting this expression, that's is W net. Next, you have to write temperatures in terms of RP value. So T1 and T4, T2 and T2 and T4 in terms of RP value you have to write. So for that, consider the process 1 to 2. So for the 1 to 2 process, already you know relationship between the temperature and pressure. So what you have, T2 by T1 is nothing but P2 by P1 to the power gamma minus 1. From that equation you will get T2 is nothing but T1 times P2 by P1 to the power gamma minus 1 by gamma. So P2 by P1 is nothing but Rp. So what you will get, T2 is nothing but T1 times Rp to the power gamma minus 1 by gamma. So this expression you will get. Note down this equation as 1. Similarly for 3 to 4 process, you have to get the expression of T4 in terms of Rp. How you have to get T3 by T4 is nothing but P3 by P4 to the power gamma minus 1 by gamma. P3 is nothing but P2 and P4 is nothing but P1. So hence you can get Rp to the power gamma minus 1 by gamma, T3 by T4. But now we have to get T4 in terms of Rp. So rearrange the term, T4 bring this side, Rp you bring this side. So what you will get? Rp is T4 is nothing but T3 divided by Rp to the power gamma minus 1 by gamma. So note down this equation is 2. So substitute these two equations, that is equation 1 and equation 2 in this equation. Make this one a star or any other number. So substitute 1 and 2 in the above equation. So you will get the net work output in terms of Rp and T1. So note down. So what you will get? W net is nothing but Cp times T3 minus T1, T3 minus T3 by Rp to the power gamma minus 1 by gamma minus Cp into T1 into Rp to the power gamma minus 1 by gamma minus T1. So this expression you will get. And now let us assume this Rp some notation, other notation, because it will writing this one will be taking more time, or it may lead into confusion. So let us assume Rp to the power gamma minus 1 by gamma as y, just y. Instead of writing this many terms, we just substitute, let us assume Rp to the power gamma minus 1 by gamma by y. So just assume. So what will become an expression? W net is becomes Cp T3. T3 is common over here, so you can take it outside. So 1 minus 1 divided by y minus Cp. T1 you can take it outside, so y minus 1. So now you got W net will be like this. So once you got the W net like this, now we have to get the maximum power output. So this is the network output. So how you can achieve the maximum work power output? Because in this equation, Cp is constant, because it will depend upon your fluid. So and Cp is constant, and T3 and T1 will be maximum and minimum temperature of the cycle. So that is also constant. Now only variable is y. So how to other all the parameters are constant, so variable is y. So how to get this maxima? So we have to differentiate this equation with respect to that variable. So here variable is y, hence we have to differentiate this equation with respect to y, and when you equate it to 0, then you will get a condition for maximum efficiency, or means a maximum power output over here. So hence differentiate this equation with respect to y. So once you differentiate with respect to y, what you will get? So differentiate with respect to y, so you will get like this expression. Cp and T3 are common, so minus, so you will get differentiation of 1 is 0, then minus 1 by y differentiation is minus 1 by y square, so minus minus will get plus. So over here it will become Cp T3 into 1 by y square minus Cp into y Cp into T1, and y will be the differentiation of y will be 1, and minus 1 will be there, so that differentiation is 0. So only this parameter will get. So Cp will get cancelled, rearrange the term and get the expression for y in terms of T1 and T3. So just rearrange the term and reduce the step, and you will get like this. That is y is nothing but T3 by T1 to the power 1 by 2. This is the condition to get the maximum work output or power output. So now you substitute back, y is nothing but Rp. You have taken that one, so y is nothing but your Rp. So substitute back, so you will get Rp to the power gamma minus 1 by gamma to the power that is equals T3 by T1 to the power 1 by 2. Now bring this term to the other side. So whenever you bring indices to the other side of the equation, then gamma will be numerator, gamma minus 1 will be the denominator. So what will become? Rp is nothing but, that is nothing but optimum pressure ratio is nothing but T3 by T2 T1 to the power 1 by 2 into gamma by gamma minus 1. So in this way you will get the expression for optimum pressure ratio. So this is the expression for optimum pressure ratio in terms of maximum and minimum temperature. You have to remember this equation also. So note down this equation, and this derivation is very important from the exam point of view. So note down the all the steps. So if you plot the graph, so this optimum, or where you will get the once the power is maximum, that means you may get the maximum efficiency also with respect to RP value. So similarly, compression also, we have the isentropic compression divided by actual compression work. Next, we have the how to uh, get the maximum pressure ratio or effect of pressure ratio on Brayton cycle efficiency. So always the exhaust temperature or maximum temperature on the turbine blade always exposed to the highest temperature to the turbine blades in around 800 to 1000 degree centigrade. So this will be your maximum cycle temperature, that is the T3. If you draw the TS diagram, this will be your maximum temperature, so Tmax, and this will be your minimum temperature, that is at point 1. So now if you increase the pressure ratios, so how it will affect your efficiency? So 1 to 2, 2 to 3, 3 to 4, 4 to 1, that represent lower pressure ratio. If you increase the pressure ratio between same temperature limit, that is maximum and minimum temperature limit. So if you have maintained that maximum and minimum temperature within this limit, if you keep on increase the pressure ratio, so what will happen for efficiency, that we have to check, or we have to get the maximum efficiency in terms of means maximum pressure ratios in terms of this maximum and minimum temperature. So if you increase the pressure ratio for the second case, see, increased pressure ratio increased, so that cycle will be 1 2 double dash, 2 double dash to 3 double dash, 3 double dash to 4 double dash, and 4 double dash to 1. So this is your increased pressure ratio compared to previous cycle. Still, if you increase, so your cycle shape will change like this. So 1 2 dash, 3 dash, 4 dash. So if we keep on increase the pressure ratio, so what will happen? The mean addition of heat temperature. Heat addition process is like this, 2 to 3. See here, temperature 2 will be at a lower condition. So hence addition of average temperature is less, whereas here 2 is increased from 2 double dash, so average heat addition is increased. See, from 2 double dash to 2 dash it is increased, so average heat addition is increased. Whereas compared to heat rejection, see, 4 to 1 is the heat rejection, so here 4 is more, so heat rejection is more in the 4 to 1 process. Next, if we increase the pressure ratio, it will 4 is reduced to 4 double dash, that means 4 double dash temperature is less than 4, and heat rejection is decreases, and 4 dash again it is decreased, so heat rejection process, average heat rejection process also decreases if you increase the pressure ratios. So you can check over here. So as you increase the pressure ratio, the heat addition is keep on increases, whereas heat rejection is keep on decreases. So now we will check the heat addition process. So temperature, average temperature of heat addition, it is given by Tm1 in terms of H3 minus H2 divided by S3 minus S2. So this is the expression for temperature heat addition. Similarly, temperature heat rejection is given by Tm2. So that is nothing but H4 minus H1 divided by S4 minus S1. So this is nothing but heat rejection process, average temperature of heat rejection. So if you increase the pressure ratio, lower pressure ratio, the mean temperature of heat addition is less, whereas as you increase the pressure ratio, so your heat addition process is average temperature of heat addition is increases, average temperature of heat addition increases, whereas average temperature of heat rejection, it will be more for your basic cycle. Then if you have increased the pressure ratio, then the average temperature of heat rejection is less, and it will become still lesser if you keep on increase your pressure ratio. So this is how it will affect your RP. So in this case, so what you have to get, so as the pressure ratio increase, your TM1, that is heat addition process, it will increases, and heat rejection process keep on decreases. Further increase, still it will increases. If you keep on increases the pressure ratio, heat addition increases till what it can increase. It can increase up to maximum temperature only, because so T2 will become T3. So till that you can increase the heat addition, and your heat rejection, if we keep on decreases, it can reach up to minimum temperature. That's it, you can't go beyond that one. So T4 it will become T1. So that is the maximum temperature and minimum temperature. So that way, till that you can increase or decrease your heat addition and heat rejection process. So once you've done that one, what will happen? It will reach its maximum value. That is nothing but, maximum value is nothing but, maximum efficiency is nothing but your Carnot efficiency. So once it reaches maximum and minimum temperature, that means your cycle has been reached for the Carnot cycle efficiency. That is the limit. So with respect to that limit, what the value of RP you will get, that is the maximum RP you can done by the system. That is the maximum, you can't go beyond that value. So once your cycle reaches your Carnot efficiency, that means maximum level is reached. So for that maximum level, what is the value of RP, that you are going to find out. That is RP maximum value we have to find out. So graph suggested, so Carnot cycle efficiency that can be reached. So with respect to that Carnot cycle efficiency, what is the value of RP will get? That is nothing but RP max. So this is about RP max. Now you have to get the expression for RP max in terms of maximum temperature and minimum temperature. Maximum temperature we are assumed, that is T3, and minimum temperature is T1. So note down this equation. Next we will get the expression. So this is what TS diagram, and this will be your relationship between RP max and Carnot efficiency. So RP max of the cycle is given by, that is something but, you know, the Brayton cycle efficiency 1 minus 1 divided by RP to the power gamma minus 1 by gamma actual efficiency. But when RP is maximum, so efficiency will be what I told, efficiency will be your maximum, that is nothing but Carnot cycle efficiency. So you can compare this one with respect to Carnot efficiency. So Carnot efficiency is nothing but 1 minus T minimum divided by T maximum, T minimum by T max. So instead of Carnot, you can write 1 minus T minimum divided by T maximum. So you can equate, so this one with respect to temperature basis, T minimum by T max. So 1 will get cancelled. So what you will get? Before that, we have already assumed that is minimum temperature is nothing but T1 and maximum temperature is nothing but T3. So just substitute back, and 1 will get cancelled, and rearrange the term, you will get the expression for RP max. So 1 gets cancelled, so this one, that is equal T1 by T3, and bring back to the this side, and you bring this to the other side. So what you will get, RP max to the power gamma minus 1 by gamma, and that is nothing but T3 by T1. So RP max you will get T3 by T1 to the power gamma by gamma minus 1. So this is the expression for maximum efficiency. So to write this step, the previous theory is needed before you writing this step. So sometimes they have asked this question also. Once you got the expression for RP opt, then RP max. Next step, you have to get the relationship between RP opt as well as RP max. So how you have to get this relationship between these two? We will go forward. So now we have to get the relationship between RP max. Now you know the value of RP optimum, then RP max. So both the cases we are represented in terms of T3 by T1. So on the right hand side, what are the common term? T3 by T1 is common, and in the numerator gamma by 1, gamma minus 1, that is the common. So now how you can relate? RP opt is nothing but RP max to the power 1 by 2. So by equating these two equations, you will get the right relationship between optimum pressure ratio and maximum pressure ratio. So just compare these two equations. You can write Rp off is nothing but Rp max to the power 1 by 2. That is nothing but Rp opt is nothing but square root of Rp max. So next step you note down. Next step you note down, that is Rp opt is nothing but square root of Rp max, or Rp max to the power 1 by 2. So this is the relationship between optimum pressure ratio and the maximum pressure ratio. So 2-3 times I have asked this question. So the two derivation, previous two slide derivations are very important. So if you understood that one, then this one will be very easy. Just comparison and get the expression for this one. So while plotting the graph, what will become? See over here, when Rp is equal to 1, that is pressure ratio is 1, then your work capacity will be 0. That means there won't be any work. So maximum pressure and minimum pressures are in the same line, or you will just one horizontal line will be there. So hence there won't be any work will be there, hence you will get 0 work capacity. And similarly, just look into this diagram. When it reaches the maximum RP max, that means you will get one vertical straight line in the PV diagram. That means again the work capacity will become 0 of the system. So when you will get the maximum work capacity, that is nothing but at the optimum pressure ratio. So when you maintain that particular value of for that system, particular optimum pressure ratio, during that time you will get the maximum work capacity of the cycle. So this is very important. That is, you have to maintain the optimum pressure ratio to get the maximum work capacity of the system. So that optimum pressure ratio is going to be very much important for maximum work capacity done by the system. So this is about capacity of the system. Okay. So next we will finish over here about today's class. We are going to finish. So next class we will move forward. That is Brayton cycle is over today's class. So next class we will move forward with how to improve the efficiency of the Brayton cycle. So three methods and combination of methods. That is three methods: intercooling, reheating, and regenerator. So these three methods we will go forward. Then combination will be there. That is intercooling with the reheat, intercooling with regenerator, or combination of intercooling, reheat, regenerator. So depending upon the combination, you can use or increase the Brayton cycle efficiency. So we will try to finish all those things in the next 1 hour or 2 hours, maximum 2 hours. Then we will move forward with the jet propulsion system. So that one class is required, 1 hour class is required. So hence we will complete these portions of this module. Then we will move forward with the problematic point of view.